Welcome to the Introduction to Calculus. I'm Mr. Stark. In this video, we'll continue topic 3, which is titled More on Limits, by working through lesson 3b, which is all about one-sided limits. We'll also talk about two-sided limits. You can follow along using this document. For your convenience, it is linked in the description. Let's get started. Let's talk about limits of continuous functions first. Notice this bit. The nice property of continuous functions is that limits pass inside them. Basically what that means is if f of x is continuous, then the limit as x approaches a of f of x is equal to f of a. In other words, you can simply substitute or plug in a for x. An example of this is if we were to take the limit as x approaches, say, 3 of some polynomial, such as x squared plus 5x plus 2. Examples of discontinuous functions include rational functions, such that the denominator is equal to 0, so therefore we have a vertical asymptote, or a rational function such that the numerator and denominator have a common factor, so there's a hole, or the integer function where function values jump. We'll see some examples of that in just a moment. Now it's time to learn about the two ways we can calculate limits, one-sided and two-sided. For one-sided limits, there are two ways to calculate those, a left-hand limit and a right-hand limit. Here's the notation for a left-hand limit. LIM, the limit, as x approaches c minus, and that's a superscript for the minus sign, but we read it as x approaches c from the left side, of f of x. When we take the left-hand limit, x approaches c, but only from the left side, from the negative side of the graph, which is why we use the negative sign. The notation for the right-hand limit is very similar. LIM, limit, as x approaches c plus, so from the right side, of f of x. Again, the plus is a superscript, and it's telling us that x is approaching c from the right side of the graph, the positive side. Understanding one-sided limits is key to understanding two-sided limits. Here's why. The two-sided limit exists if the left-hand and right-hand limits exist and are equal. We've used the notation for a two-sided limit already, which is the limit as x approaches c of f of x. But notice how similar it is to the one-sided limit notation. It just doesn't include the superscript of a minus sign or a plus sign. If the one-sided limits are not equal to each other, then we say that the two-sided limit does not exist, or DNE. And that's it. Let's try a few examples. First, we'll do a one-sided limit, then we'll do a two-sided limit. Let f of x equal the greatest integer function. Find the limit as x approaches 4 from the plus side. Notice that little plus sign is a superscript of f of x. So I graphed it for us to work, and you're welcome to graph it on your own calculator as well. But what we would do first is locate x equals 4. And just a side note, when you plug in x equals 4 into the greatest integer function, or integer function for short, the result is 4. If you plug in 4.2, the result is also 4. Basically what it's doing is it's returning the greatest integer that's less than or equal to what you plug in. So really it's just like chopping off the decimal. If you plug in 3.9, you get 3. So let's go to that point on the function, which is 4, 4. Let's actually place our writing utensils at that point. But then, because it says x approaches 4 from the plus side, we'll move our writing utensils to the right so that we could actually do that. So we could approach 4 from the right side. So let's let x approach 4 while we're on the function and see where that point takes us. Notice that it takes us to a function value of 4. So the limit as x approaches 4 from the plus side of f of x is 4. Let me say it a different way. As x approaches 4 from the plus side, or from the right side, the function's value is approaching 4. Now let's do the two-sided limit. Let f of x equal the integer function. Find the limit as x approaches 4 of f of x, which is a two-sided limit because there's no plus or minus in the superscript of 4. We'll start by doing a similar thing. We'll go to x equals 4, then up to the function. We'll move to the right and then approach x equals 4 from the right. So we've confirmed that the right-hand limit, again, is 4. Now we have to find the left-hand limit. We do that by going to x equals 4, go up to the function, which again is 4 comma 4. But this time we move to the left, which forces us to jump from a y value of 4 to a y value of 3. We can move as far left as x equals 3, but then turn back around and approach x equals 4 from the left-hand side. By doing that, notice that the function's value approaches 3 instead of 4. That means the left-hand limit is 3. In this case, the left-hand limit exists. It's 3. The right-hand limit exists. It's 4. But because 3 is not equal to 4, the two-sided limit as x approaches 4 of this function does not exist. These are great examples because you can see that at every integer value for x, the two-sided limit does not exist. But if we wanted to find the two-sided limit of something like 2.5 or negative 3.6, then the two-sided limit does exist because in that little window, like in between the integers, this function is continuous. It's just that every integer, it's not continuous. Just remember, when you're calculating limits, you're always moving along the function. And it's okay if the function's value is not equal to the limit. Well, that's the end of lesson 3b. I hope you're getting fairly comfortable with limits. In the next lesson, lesson 3c, we'll cover infinite limits. Limits in which x is approaching infinity or negative infinity, or the result of the limit is infinite. As always, thank you so much for watching. If you have any questions or comments, feel free to add them below. Thanks a lot.